In this problem, we're asked to look at an experimental set of experimental results, putting a uniaxial test on the specimen. During these tests, we were able to measure through strain gauges what epsilon x and epsilon y is. Again, the loading is along x, and so the strain, epsilon x is the axial part, epsilon y is the transverse part. And what we want to do is be able to back out from that, knowing the cross-section of the specimen, what the values are for the Young's modulus and the Poisson's ratio. I'm going to go back to our basic equations here, our Hooke's law for cases in general, where epsilon x is equal to 1 over e sigma x minus nu sigma y plus sigma z. So since we're looking, I guess also we'll say in general there's an alpha delta t. So this case here has a uniaxial load, so we have only sigma x. So sigma y and sigma z are equal to 0. We're not running the test under any change in temperature, so the right-hand side reduces down to the usual form here of sigma x divided by e. So from this we get that the Young's modulus E is equal to sigma x divided by epsilon x. Sigma x is our loading P divided by the cross-sectional area A. Epsilon x, we know that. A, cross-sectional area is 1 times 0.5, and that's in terms of inches squared. I'm going to pull down the second equation that we usually see for Hooke's law. So this is going to be 1 over e sigma y minus nu the quantity sigma x plus sigma z. And in general, there is the thermal term here in the end. But again, since we're running our test under constant temperature, we have no sigma y. We have 0 value there for sigma z. So this becomes a minus nu sigma x divided by e. So from this, we can see that nu is equal to e times epsilon y, the negative sign in front, divided by sigma x. And so we already have our value for e from before. We know that epsilon y is equal to the minus 0.0008. So this is going to end up being a plus SIGN sign with all the known information. So here's just a very straightforward application of Hooke's law for the case where we don't have a change in temperature, and Hooke's law for the uniaxial loading such that we just have sigma x, then sigma y, sigma z are both equal to 0.